or we can wait. Nicolau, shall we start or we wait? Yes, okay. Okay, so good morning everyone. In the lecture of today we are going to cover gamma ray astronomy. As I will show you in a few days, gamma rays are very interesting cosmic particles that we can use to try to search and find dark matter signatures. And the main reason why gamma rays, and in particular in general radiations, also radio, X-ray, and the different wavelengths are so interesting for indirect dark matter searches, is that photons go straight in the universe and in the galactic environment because they are not affected by magnetic fields. And so with gamma rays, you can really do astronomy, so you can really point an astrophysical target that you think it's interesting for the search of dark matter. So as we will see, for example, the galactic center is probably the predicted highest density direction where we can search for dark matter. And so with gamma rays, you can really point the center of the galaxy and try to find a signal. But there is an issue with gamma rays. This issue is that we cannot detect directly gamma rays on the ground. So if we build an experiment on the ground, a telescope on the ground, gamma rays are not detected directly. Okay, you only have indirect ways to detect gamma rays on the ground. The reason is very simple. Basically, you have different processes that destroy the gamma ray when this enters into the atmosphere. You have pair production, you have Compton scattering, and just to give you some numbers, the penetration depth of gamma rays is of a few milligram over centimeter cube. No, sorry, is a few grams over centimeter square. But the atmosphere is 10 kilometers with an average density of 1 milligram over centimeter cube. So if you multiply this for 10 kilometers, you can see that basically this number is incredibly higher with respect to the typical penetration depth of gamma rays. So the atmosphere is basically a very, very thick shield for gamma rays. So there is no way for gamma rays to be detected directly on the ground. And so what we typically do to detect gamma rays directly is to build telescopes, like for example Fermilat. Fermilat has been launched in 2008, and the discoveries and the papers of Fermilat and also of other groups using Fermilat data has revolutionized our view of the gamma ray sky. And so today I don't see the, let's take the pointer, I don't know where it is. Yeah, yesterday there was the, okay. So what, great. Well, actually, in Torino, we are used to this analogic pointer. So basically, so Fermilat is made by a box with silicon layers. You have an anti-coincidence layer on top that is able to disentangle between cosmic rays and gamma rays. And when a gamma ray enters from the top of the experiment, there is a conversion of basically pair production of gamma ray into a plus and minus, and then there is a calorimeter on the bottom that measures the energy. So with the calorimeter, you measure the energy. With the conversion foil and particle tracking detector, you reconstruct the directionality of the positron and of the electron. And so, combining energy and directionality, you can reconstruct the energy of the initial photon. Fermilat is able to measure the gamma rays between 100 MeV up to almost 1 TeV with an angular resolution that is between 0.1 degree up to a few degree. and with an ROI that basically covers the entire sky in a few hours. Instead, if you want to detect higher energy gamma rays, you really need to go on the ground. And the main reason is that if a gamma ray of, let's say, 10 TeV enters inside the Fermilab detector, the conversion could even not happen in the detector, because basically the photon is so quick, is so fast that go through the detector, or the conversion is too close to the calorimeter to reconstruct the directionality. So in order to detect a 10 dV gamma ray, you basically need a Fermilat that is at least a factor of 10 or 100 larger. So the alternative is to use instead telescopes on the ground, then measure the Cherenkov light emitted by the particles produced after the shower. So the gamma ray enter in the atmosphere, interact with the atoms, creates secondary particles, pions, muons, electrons, positrons. These particles travel faster than the velocity of light in the atmosphere and generates a Cherenkov light. And these telescopes are made of mirrors and photomultipliers that detects this even faint Cherenkov light and reconstruct the energy of the initial gamma ray. With imaging air Cherenkov telescopes, you can measure even almost 1 PV gamma ray with a much better angular resolution and energy resolution. Okay. Okay, very good. There is another very important point that it will be useful for the rest of the lecture, that is the gamma ray absorption. So when you have very energetic photons, so basically photons gamma ray with an energy above 100 GeV, these photons interact with the CMB. And this creates a couple of electrons and positrons. So very energetic gamma rays are lost because of the interaction of the CMB. So this is a sort of absorption that we have to take into account, and we will take this into account using an exponential factor of minus tau gamma gamma, that is basically, it's a sort of absorption factor. And the exponential, it's giving you basically the probability or the absorption factor for the flux of gamma rays. So typically, if you have an extragalactic source and you plot E squared flux, if you have something like this, above 100 GeV, you start to see an exponential cutoff that basically cuts completely the flux, let's say, above 1 TeV. And in this plot, you see the typical propagation length for a gamma ray. And you can see that for 1 PV photon, you get the minimum for the lambda factor that is of the order of the distance between the Earth and the galactic center. So if you have a 1 PV gamma ray, you can just prove your galaxy, you can just prove the Milky Way. So it's impossible to do extragalactic gamma ray astronomy with gamma ray photons, because they are basically completely absorbed when they come from outside our galaxy. So when we do gamma ray astronomy with extragalactic sources, we have to take this into account. Okay, perfect. Now we talk about one of the main source of non-thermal emission, so from basically radio to gamma ray that we have in our galaxy. We already touched this galactic source yesterday when we were talking about acceleration of cosmic ray, and these are supernova remnants. Okay, so a supernova remnant, a supernova explosion is generated when you have a star with at least, let's say, 8 solar masses that after millions or billion of years, depending on the temperature and the size. Basically, it ends the nuclear fusion because the star does not have any more hydrogen to make the fusion. And so the gravitational force wins against the pressure of the nuclear fusion. So you have a contraction due to gravity and then an explosion. This explosion generates roughly 10 to 51 erg of energy, and the material moves away from the center with a velocity that is between 10 to 3 and 10 to 4 kilometers per second. Now, the dynamic of the supernova depends on the eject mass, so basically the mass that is ejected from the supernova, and the swept out or the swept up material that instead is the material that the supernova shock encounters in the interstellar medium. The difference between these two masses will drive what happens to the supernova. And there are basically three phases. The first phase, that is the most powerful, that is basically for an age below roughly 1 kilo-year. In this age, you have the eject material, it's much larger than the swept out material. The supernova is increasing in size very quickly, so linearly with time, with a velocity that is very, very large, a fraction of the speed of light, and you start to have the supernova shock that we saw yesterday that starts to accelerate particles. In the second phase, the shock waves start to decelerate. This is also called the Sedov-Taylor phase. And this happens between, let's say, 1 kilo-year up to 30, 40 kilo-years, depending on the characteristic of the supernova. The shock wave starts to decelerate. The increase of the size is not linear in time, but is t to the 2/5. And you start to, basically what happens is that the shock starts to feel efficiently the interstellar medium. Okay, so you have to imagine this explosion. Initially it's very, very fast, but then after some time it starts to decelerate. You start to feel the gas and interstellar medium. And exactly as what happens if you throw a ball against a wall, this shock wave encounter the interstellar medium and you start to have a reverse shock. Okay, so the reverse shock that you see here. So you have the forward shock. This encounters interstellar medium material, and this creates a reverse shock that goes towards the center. And this reverse shock will be very important for pulsar wind nebula. So you have a forward and a reverse shock, and they both start to create non-thermal emission and production of photons from radio to gamma rays due to synchrotron, Bremsstrahlung, and inverse Compton scattering. In the late phase, that basically is between, let's say, 40 kilo-years up to 100 or a few hundreds of kilo-years. In this phase, the mass of the ejecta is much smaller with respect to the mass of the swept out material. And basically what happens is that the supernova and the shock wave dissolves into the interstellar medium, and the acceleration of particle is not efficient anymore. Okay, these are the three phases. These two phases are very, very important for the acceleration of particles and for the non-thermal emission. We saw yesterday that the diffuse shock acceleration in supernova remnants accelerate particles to very high energy with a slope roughly of 2. And we saw also yesterday that it's still not clear exactly basically if the emission of particles from supernova is of hadronic, leptonic, or what fraction of hadronic and leptonic acceleration you have in the different supernova remnants. Okay, so now we will focus our analysis on the hadronic interactions. Okay, so we study the production of gamma rays in supernova remnants due to the interactions of cosmic rays accelerated from the supernova that hit the atoms of the interstellar medium, and due to these nuclear interactions, you have the production of pi zero that decays immediately in 2 photons. Okay, this is the main, one of the main source related to the hadronic process in supernova remnants. So when we talk about nuclear interactions, we talk about the strong force. So this is the force that basically is responsible for the production of pi zero particles. This is a very short time scale interaction that basically happens between, let's say, 10 to the minus 15 seconds and a few femtometers. And we can just make a very rough estimation of the cross-section by taking the geometrical cross-section. So we take the nuclear size that depends on the atomic number A of the atom of the interstellar medium. This is roughly of the order of femtometers. The larger is the nuclei, and of course the larger is also the size, the radius of the nucleus. And so the geometrical cross-section is simply pi r squared, and this is roughly 45 A 2 over 3 millibar. Okay, so when we talk about interactions with the strong force, we are talking about tens of millibar. Okay, this is roughly the order of magnitude we are interested in. And now, using the cross-section, we can estimate the typical time scale for a cosmic ray to hit an interstellar medium atom and make this production of pions. And this is roughly equal to 1 over the density of interstellar medium atoms, the geometrical cross-section, multiplied for the velocity of light. And if you plug in the numbers, this is roughly 25 atomic number. Of course, depends on the density of the interstellar medium, that is roughly of the order of 1 centimeter cube, mega year. Okay, so the typical time scale for these interactions is tens of mega year. You probably remember yesterday from my lecture and also from the exercise session of Pedro that the typical time scale for diffusion of cosmic rays is of the order of tens of mega year up to 100 mega year. Actually, for a 10 GeV particle, 10 GeV proton is 100 mega year. So this time scale can be even smaller than the typical time scale of diffusion. So this demonstrates how including these nuclear cross-sections is very important for the propagation of particles. Okay, now, so what we are talking about is a cosmic ray accelerated by the supernova and hitting interstellar medium atoms located around the supernova. And so we're talking about processes like this. And as yesterday we saw, cosmic rays are basically dominated 90% by protons, and interstellar medium is dominated by 90% of hydrogen atoms. So basically, most of the process is a proton colliding against an hydrogen. So basically, for this cross-section is a proton against another proton, producing pions. So you can have this process that creates a pi zero, pi plus, pi minus. These are the dominant processes. We are interested in this one that generates pions, but I also wrote these other two with pi plus, pi minus, because pi plus, pi minus then decays into muons, then you have neutrino muon, this mu minus, neutrino, antineutrino minus, then this one decays into positron, neutrino, electron, and then you have also the neutrino muon, and this E minus, antineutrino electron, okay? So this chain of decay basically makes for every collision you have a lot of neutrinos, okay? So it's typical of hadronic interactions to have the production of gamma rays and neutrinos. So if you have an experiment that measures precisely the neutrino flux at more or less the GeV scale, you can verify very precisely if your source makes hadronic or leptonic acceleration, okay? At the moment, we are not still there because, as you know, IceCube, KM3net are focused more into the very high energy, ultra high energy neutrinos. But in principle, if you make a neutrino experiment very sensitive to, let's say, GeV, tens of GeV, 100 GeV neutrino, you can really disentangle between leptonic and hadronic interactions in supernova remnants. Okay, now, what is the threshold for the incoming proton to generate a pi zero? This can be calculated very easily with relativistic kinematics, and the threshold for the proton of cosmic ray to generate pi zero is of the order of 1.2 GeV, or if you want, a kinetic energy roughly of 280 MeV. And as we know, cosmic rays accelerated by supernova remnants are really able to exceed by far this energy. In addition to those processes, you also have several other processes that can generate pi zero particles. With our colleagues, Fiorenza Donato, Luca Urusa, we embarked a few years ago in evaluating the cross-section for the production of pi zero for all these different channels. The pi zero is the main one, but actually pay attention that you also have K plus, K minus, K zero short and long, and you also have hyperons and dieta particles. So if you really want to have a cross-section that includes all the possible production of pi zero, the effort that you have to devote is quite significant. Then luckily, we have a lot of data for the production of pi plus, pi minus, but unfortunately, the data for the production of pi zero are very rare. But there is a lot of effort in the community to have new measurements for the production of pi zero. Okay, so it's clear that if we want to parameterize this kind of productions, we have to calculate the cross-section. So we have to calculate the cross-section for proton-proton producing pi zero and whatever, okay? And this is typically calculated with the Lorentz invariant cross-section that depends on three kinematic variables, for example, the center of mass energy, the transverse momentum, and then you can typically choose XR or X Feynman. And this cross-section, it's very important to notice that it cannot be found from first principle, okay? So at the moment, we don't have first principle theories that predict these cross-sections. And what we typically do is that we use analytic functions that are functions of these variables, and we fit these analytic functions to data. If you're lucky, you have a very diverse, very rich data set. If you are in this situation, you can fit well your parameters. In other cases, for example, the production of pi zero, the data are very rare, and so you have to use some tricks that I will show you in a few minutes. And typically, this is parameterized with the sigma proton-proton inelastic because the process is an inelastic process, multiplied for a function that is the function that we actually fit to the data that depends on the same parameters. Okay, so this inelastic cross-section keeps a dependency on the center of mass energy, but all the other parameters, PT and XR, XF, are in this function that is fitted to the data. Now, regarding the inelastic cross-section, what is typically done in the community is that we typically use the total proton-proton cross-section, that is the black curve and data, and the elastic, that is the blue, and by difference you find the inelastic. And we do this because data for inelastic are not very precise and are not so many. Instead, for the total and elastic are much more numerous. And so what we do is that we fit analytically the total and the elastic, and by difference you find the one for the inelastic. But for the basically for the analysis of cross-section scattering, nuclear scattering in supernova remnants, typically we don't use the full Lorentz invariant cross-section with all the dependency with these three kinematic variables, but we use the inclusive cross-section. The inclusive cross-section, proton, proton, pi 0, x, depends only on the square root of s, and so basically depends only on the incoming proton energy. And this is basically proportional to an integral in the kinematic variables pt, and typically there is an angle to integrate of the Lorentz invariant cross-section. Okay, so this is typically what is done, and we just use the inclusive cross-section. The inclusive cross-section increases only logarithmically for, let's say, proton energies above a few tenths of GeV. So we have to keep this, yes? The integral here. So the integral here is an integral in the two kinematic variables that we are not interested in. So the PT, for example, and the angle, and PT and angle is basically equivalent of removing XR or XF. Okay. And the important thing to remember for the rest, for the next minutes, is that the inclusive cross-section does not depend so much on the center of mass energy. So it increases only logarithmically with the center of mass energy. Okay. Then, as I was saying before, for pi 0, we don't have a lot of data. And so typically we take the inclusive cross-section for pi 0 as an average of the cross-section for pi plus the cross-section on pi minus. For pi plus, pi minus, actually we have a lot of data for different energies, from low energy to very high energy. And this approximation should work well for, let's say, proton energy of at least 1 TeV, where the pi plus, pi minus, and pi 0 cross-section should be quite similar, and so a simple arithmetic average should work well. For low energy, this could be not a very good approximation. Okay. Okay, now we do some more mathematical calculations, and we try to calculate the main dependencies in the emissivity. First, we will evaluate the pi 0 emissivity. Then we will make pi 0 decay into 2 photons, and we will evaluate the photon emissivity. So the pi the pion emissivity that depends on the pion energy. This is roughly basically is the source term that you can put in the propagation equation. Is the velocity of light, density of hydrogen. Then you have the cross-section that we saw before. You have the flux of incoming cosmic ray protons that depends on the proton energy. And then you have a delta function for the pion energy minus k pi t pi proton, integrating in the proton energy. So you have to include the flux or like the spectrum of cosmic ray proton colliding against the atoms of the interstellar medium. Everything is averaged over the cross-section. And this factor is something that we include just to simplify the calculation. Yes? The background. The background, you mean the atoms on which the the collision is happening, or? Ah, no, the problem, so experimentally it's difficult to measure the pi zero cross section simply because the pi zero is neutral. Okay, so for example, also cross section for the production of neutrons are difficult to measure experimentally. So every time you want to measure proton-proton into a neutral particle, this is experimentally quite challenging to measure. So it's not a matter of background, but just the pi zero and the neutron, our neutral particle, and so it's challenging to measure these cross sections. Okay. So typically, experimentally, what is done to measure the pi zero production is that you have to target the production of 2 photons. Okay, the production of 2 photons is easier to measure experimentally. So you have to build an experiment that every time you have 2 photons with the right coincidence, then you reconstruct the energy of the pi zero. Exactly. Yeah, yeah. Yeah, exactly. But this is much more difficult with respect to measuring directly pi plus, pi minus that are charged particles. So you can use a magnet to see the curvature. So in this case, unfortunately, it's more difficult. And so here we put this delta that is just for simplification. When you do a complete calculation, this is not included. And this K is the inelasticity factor that is basically telling you that the kinetic energy of the pion is a fraction K pi of the energy of the proton. And this inelasticity factor is roughly equal to 0.17, okay? So this implies that you have some distribution for the pion energy. This distribution is something like this, and we just take the peak. And the peak is at 0.17 times the kinetic proton energy. Using this delta function, of course, we can remove the integration, and we find that the pion emissivity is Cn hydrogen k pi sigma proton-proton evaluated for T pi K pi plus M proton, and then you have the proton okay. Now we can assume that the energies we are talking about are much larger than the proton energy. So we are talking about incoming protons of energy, let's say beyond above 10 GeV, and so we can neglect this plus mass of the proton, and we can so rewrite this as C and hydrogen elasticity, proton pi 0, that depends only on E pi divided by K. And then you have the proton spectrum, E pi, K pi, okay? Now, there are two important consequences of this. The pion emissivity, or the source term for the interaction of cosmic ray with interstellar medium atoms, depends on the initial proton spectrum with the same slope, because let's keep in mind that this is proportional to the energy to the minus gamma that comes from the diffuse shock acceleration. So the source term of the pion is inheriting the same slope from diffuse shock acceleration. And since the slope of the proton-proton pi 0 cross-section is basically flat for very high energy, the final emissivity has the same slope of the incoming proton. Okay? So the shape of the pion is basically more or less the same of the initial proton. Now we have to deal with the decay of the pi 0 into 2 photons. This happens at a very short time scale because of the strong force. If we take in the center of mass of the pi 0 the energy of the photon, it's simply the mass of the pi 0 divided by 2. This is in the center of mass. If we want to instead do the case where the pi 0 is moving, what we can do is that we apply a Lorentz boost. So a gamma equal to mass pi divided by 2 gamma pi 1 plus the beta factor and the cosine of theta. So the beta factor is simply the velocity of the pi 0 divided by the velocity of light. The gamma factor is the one of the pion. And the cosine of theta, theta is the angle between the direction of the motion of pi 0 with respect to the emission of the photon. Okay, this is the theta angle. For the cosine of theta, we have two, let's say, very different values that you can put, plus minus 1. This will give you a minimum and a maximum energy for the photon. So E gamma min max can be found by doing m pi divided by 2 gamma, and then you have 1 minus plus beta. So now let's do two cases. First, we do non-relativistic case. In the non-relativistic case, how much is the E gamma? Non-relativistic case, gamma is equal to? Beta is equal to? So E gamma is equal to? Is m pi divided by 2. So it's equivalent of the center of mass case. So E gamma minimum is equal to E gamma maximum, mass pi divided by 2. And then we can do the relativistic case. In the relativistic case, or like the, in the relativistic case, we have two separate, two basically opposite cases, where you have beta that is equal to 1. Let's do the ultra-relativistic case, where beta is equal to 1, okay? So for beta is equal to 1, you can have minus in the minimum case, and the energy is equal to 0. Or you have the maximum, where beta is equal to 1, but you have the plus, and you have gamma m pi divided by 2, okay? So this is equivalent of having basically E pion, okay? So in the ultra-relativistic case, the two very opposite cases is where the gamma is equal to 0 or the one is equal to the pion mass, the pion energy. Well, this is not very surprising, right? But now we try to do a step forward. and we calculate the distribution of photons. So we can differentiate the E gamma. So we have d E gamma is equal to m pi divided by 2 gamma beta, and then you have d cosine of theta. And this is the differentiation of the photon energy. And we want to do the distribution of these photons. And so we have to evaluate what's the distribution in space of the photons. So can you imagine what's the distribution of photons basically in the reference frame of the pion, the pi zero? The pi zero is a scalar particle, and so the photons are emitted isotropically. This means that the distribution of photons in angle is the one of an isotropic production, so it's basically homogeneous in the 4 pi. So it can be written in this way. So if we rewrite this differentiating over cosine of theta, we have this. And now we can do the ratio between the two quantities. So we can do dn over dE gamma, that is equal to 1 mass pion, gamma pion, and beta pion. And writing explicitly the gamma factor, we have 1 over energy of the pion squared minus mass of the pion squared. Okay? Okay. Okay, let's take 1 minute to think about this equation. So this is the distribution of the energy of the photon as a function of the pion mass, of the pion energy. If we fix the pion energy, the distribution of the photon energy is constant, right? It's flat. There is no change of dN over dE gamma if we fix the pion energy. So if we do a plot like this, so with dN dE gamma, if we fix the pion energy, the distribution is flat. It's flat and it stays between 0 and the pion energy. So what we expect as a result is to have a photon flux that is a box shape. Okay, it should be something like this. We expect then a cutoff low energy because of the kinematics, because of the threshold of the protons. For higher energy, we expect something like this because, of course, the pion energy is not fixed. The incoming proton energy can reach even PV, so we expect a tail at high energy because of the proton that can reach even very, very high energy. Okay, so this is more or less what we should expect. With an average, so the average of the logarithm of the photon, that should be the logarithm of the mass of the pion divided by 2. So we expect that, let's say, the peak of the box should be roughly equal to 68 MeV. Okay. Okay, now we can do the last step to reach really the gamma ray emissivity. We can write the gamma ray emissivity, that is a function of E gamma. We use basically the same procedure as before, so we integrate in the pion energy, and we integrate the pion emissivity multiplied for dN over dE gamma. And here we add a factor of 2 because each pi zero produce 2 photons. Then we can plug in the numbers for the different quantities we have before. So basically we can put here the q e pi. The spectrum is given by that equation. And so what we can see is that the spectrum of photons should have a box shape spectrum, and it should inherit the slope of the pi zero. But let's keep in mind that the pi zero was inheriting the slope of the proton. How much is the slope of the proton? 2, right? So if we do a plot in E squared emissivity of the photon, this is expected to be flat because it's e to the square. It should go down here because of kinematic cutoff, and it should have a tail at high energy due to the proton energy can reach very, very high energy, okay? With an average of the order of 68 GeV. Okay, this is in theory. What do we have experimentally? In reality, we have something that is of the order of what I said, okay? So this is the plot for a specific source. The pion decay is the long blue dashed curve. So it's this curve here, blue. Is in fact a box shape with the low energy cutoff at basically 10 MeV. So the peak of the distribution is exactly where I said. And then you have the high energy tail that is due to the fact that you have very high energy protons. This is another plot for other 2 sources detected by Fermi. This was a science paper by Fermi where there was one of the first evidences of the hadronic production of pi zeros. And here you can see also how difficult is to disentangle the inverse Compton and pi zero production. So what you expect from inverse Compton is not a box shape, but it's something that is harder with respect to the pi zero. So if the pi zero is flat in E squared DND, inverse Compton is expected to have a slope smaller than 2, so something like 1.5, 1.8. But here you have data that at very low energy. So you need data basically around 100 MeV. And unfortunately, Fermilat is not that sensitive at these energies. So at the moment, the identification, what happened? Okay. So at the moment, the exact identification of the process that produces non-thermal emission, if it is hadronic or leptonic, is challenged by the not, let's say, not very good resolution and sensitivity of Fermilat at around 100 MeV. Okay, let's see if I am in time. Yes, perfect. Okay, any questions so far? No? Okay, let's do the following. Let's make 5 minutes of break now, okay? And then we reconvene. Okay, so let's restart the lecture. Now we move to another source, in particular another galactic source that is very important for the acceleration of cosmic rays. These are pulsar wind nebulae that are related to the pulsar, that are connected to what is a neutron star. So the neutron star is what remains in the center of a supernova explosion. So when the supernova explodes, in the center of the supernova, you have a neutron star. The neutron star is a very extreme object that is of the order of 1.4 solar masses with a diameter of Manhattan. Okay, so with the diameter of a city. The fact that you concentrate so much mass into such small volume makes these objects extremely, extremely powerful. And I will show you more properties about pulsar in a few tens of minutes. These objects are interesting for the acceleration of positrons and electrons, and these have been found for the first time by the detection of an extended emission around Geminga. And in particular, this was detected by Milagro. Milagro found an extension of the order of 2 degrees of very high energy gamma rays. And then Hawke detected also confirmed the extended emission around Geminga and found also an extended emission around Monogem. In this map, you can see this result by Hawke. This is actually not the original paper of 2017. This is a new analysis done last year. Monogem and Geminga are actually close in the galaxy, and the extended emission is very bright. You can see here the degrees, so we're talking about a few degrees of extension. They are the most promising objects for accelerating local positrons. And then nature decided to put these two sources, one close to each other, just to complicate our analysis. And this is not the best that nature could have chosen, because if you analyze the gamma ray flux as a function of distance from the source, here it's in parsec, you see that you have the light green that comes, in this case, for Geminga, and you have the contamination of Monogem. Okay, so this is not the best to do analysis and disentangle the emission of Monogem and Geminga. But at least we have experiments that can measure the gamma ray flux from these objects. This discovery is very important for a few reasons. One is that these very high energy gamma rays, so we are talking about energy beyond basically 100 GeV, and that reach even almost 1 PeV. These gamma rays are generated very likely by inverse Compton scattering or very energetic electrons and positrons colliding against interstellar radiation field. And this collision upscatter the interstellar radiation field to gamma ray energy. So by measuring and the flux as a function of energy, but also the flux as a function of distance from the source, we can have an estimate of the source term for the production of positrons and electrons from the pulsar wind nebula. Of course, in an indirect way, because we detect the gamma rays produced by this collision. The second very important point is that this flux as a function of distance from the source is compatible with an inverse Compton production only if the diffusion around the pulsar wind nebulae is of the order of the average diffusion in the galaxy divided by a factor between 100 and 1000. So it seems that around pulsar wind nebulae, the diffusion coefficient is inhibited. Now, inhibited seems that it means that the diffusion is not acting in a powerful way, but actually it's the opposite. Because if you have a small diffusion coefficient, so the average of the galaxy is 10 to 28 centimeters square per second. This one on the pulsar wind nebula is it's, let's say, 10 to 26. But having a smaller diffusion coefficient means that you have more confinement power, okay? So if you would put here the case with 10 to 28, the flux is expected to be something like this. So quite flat. This is why 10 to 28 is not consistent with the data. So you need to decrease the diffusion coefficient and make it actually more efficient to contain the positrons and electrons around the pulsar wind nebula. And it's one of the biggest theoretical challenge in astroparticle physics is to explain why around pulsar wind nebula you have an inhibited diffusion. The third reason is that using these observations, you can find the possible pulsar contribution to the positron excess detected by AMS. So we saw yesterday this. We have the data of AMS for the positron. The astrophysical production of positron is the green line. There is a very big excess, and pulsars are probably the most reasonable source of these high energy positrons. Okay, so since it's important for these processes, the inverse Compton scattering, we have to study this process. Before studying the inverse Compton scattering, we study the Compton scattering. And we start with the classical treatment. In the classical treatment, you have the classical treatment of the Compton scattering. You have an electromagnetic wave, a photon, that interacts with an electron or a positron and makes the electron and the positron to oscillate, and the oscillation of the electron or the positron generates radiation. So we have to write mathematically the Poynting flux. The Poynting flux is the vector product of magnetic field and electric fields. This can be rewritten just considering the electric fields. In case you have an electromagnetic wave, we know that the electric field can be written with an oscillating function, so a sine of omega t plus phi. And the electromagnetic wave oscillates the electron, and so you have to take into account the Lorentz force that, in case you only have, we consider an electric field, is given by this equation here. This can be rewritten also with the mass multiplied for the acceleration, and so we can write that the acceleration is equal to force divided by mass. And we can make an average over time of the acceleration squared that is equal to q squared mass squared the amplitude of the electric field squared divided by 2, where the 2 comes from the average of the sine. Okay, averaging in time for the sine, you have the 1 over 2. And so now we can evaluate the average power emitted by plus and minus, and we can get the so-called Larmor equation, that is the classical treatment of the power of radiation emitted by a charged particle under an electromagnetic field. And what is important to stress here is that this can be used for both synchrotron radiation and inverse Compton scattering, because for synchrotron radiation you have a magnetic field. For inverse Compton you have a photon, but they are both electromagnetic waves. And so this gives 1 over 3 charge for power m squared C3 is 0. And finally, we can get the cross-section as a ratio between the power and the Poynting flux. And this gives the famous Thomson cross-section, that is the classical treatment of the scattering between an incoming electromagnetic wave, in particular a photon, against an electron that is at rest. And the power is calculated as the Thomson cross-section, velocity of light, and the energy density of radiation. Okay, so this is the classical treatment of the Compton scattering when the power of radiation emitted by electron is proportional to the Thomson cross-section and to the energy density of radiation. In the relativistic treatment of the Compton scattering, we are considering a photon with a wavelength lambda interacting against an electron that is at rest. The photon is scattered with a different wavelength at an angle theta, and the electron is upscattered with some kinetic energy. You can solve this problem with simple relativistic kinematics, and you can find the famous equation for the final energy of the photon with respect to the initial energy of the photon, 1 plus epsilon I, that is the initial energy, MAC squared, 1 minus cosine of theta. Okay? And we can write what's the difference of energy with respect to the initial energy. And this is roughly equal to minus epsilon I MAC squared 1 minus cosine of theta in the regime where the epsilon I is much smaller than MAC squared. So in the regime where the initial photon energy is much smaller with respect to the rest mass energy. This is also called the Thomson regime. In the Thomson regime, you can use for this scattering the Thomson cross-section, while instead in the Klein-Nishina regime, that is the case where epsilon I is much larger with respect to the rest mass energy of the electron, you have to use the Klein-Nishina cross-section. What's the difference between the Klein-Nishina and the Thomson? We can evaluate this by developing over the Thomson cross-section. And we evaluate this as a function of x, that is the ratio between epsilon I and MAC squared. Okay, now what we can conclude from this Klein-Nishina cross-section? X is the ratio between the initial energy and MAC squared. In the Klein-Nishina limit, the energy of the incoming photon is much larger than MAC squared, so X is larger than 1. And so the Klein-Nishina cross-section is a suppression of the Thomson cross-section. This will be very, very important for the energy losses of E plus E minus. Because if you just take the Thomson cross-section, you have a value, but for the Klein-Nishina, the cross-section goes down. So you have a reduction of the cross-section in the case of the Klein-Nishina limit. But what I said so far is related to the Compton cross-section. so where the electron is at rest. But in the case of the pulsar wind nebulae, it's the opposite. So the electron and the positron are very energetic, and they scatter low energy photon fields that are the ones of the interstellar radiation field. And so we cannot use the Compton scattering, but we have to do the inverse Compton scattering. In this case, you have an incoming positron, for example, that scatters against a photon of the interstellar radiation field. You have the scattered positron, and the photon is upscattered to gamma ray energy. So it's at least, let's say, above GeV energies. Okay. Interstellar radiation field photons can reach at most, let's say, 10 electron volt. If I remember, the starlight peaks at a few electron volt, so at most you can reach 10 electron volt. So what is happening in pulsar wind nebulae cannot be reconciled with the Compton cross-section, but you really have to take into account the inverse Compton cross-section. In order to calculate the inverse Compton cross-section, we can take the equation there for E final with respect to E initial, and we can do a boost for the incoming photon in order to make, to change basically from the Compton scattering to inverse Compton scattering. And by doing this boost, you can find that the final energy of the photon is roughly equal to gamma squared initial energy, that is roughly equal to energy of incoming photon in electron volt, the electron energy in GeV squared, and this is in units of MeV. Okay? And also in this case, we can talk about the two different cases. So you have the Thomson regime and the Klein-Nishina regime. In the Thomson regime, basically you have that gamma epsilon I is much smaller than MAC squared. In the Klein-Nishina regime, instead, you have that gamma epsilon I is much larger than MAC squared. And in particular, epsilon F, so the final photon energy, is roughly equal to the electron energy. Instead, in this case, the final energy is roughly equal to the initial energy. So you have these two very separate cases, where in the Thomson regime, the energy lost by the electron is not that much, so the final photon energy is roughly equal to the initial one. Instead, in the Klein-Nishina regime, the final energy is roughly equal to the electron energy, so the electron loses most of its energy. So, as you can imagine, reality is between these two cases, and so you really have to take into account inverse Compton scattering for the radiation emitted by electrons and positrons, and also for the energy losses. In order to evaluate the energy losses for inverse Compton, we can write the energy losses first in the Thomson regime, basically first in the Compton scattering. So we said we saw before that this is what happens for the Compton scattering. Then you can do a boost. Basically, this is actually equal to dE over dt for the inverse Compton scattering, because dE over dt is a Lorentz invariant. And you can make a boost from U, a Lorentz boost from U in the reference frame of the electron at rest to the case where electron actually is moving. And if you do this boost, you find that U prime radiation, where electron is at rest, is gamma squared 1 plus beta factor of electron, U radiation, where now you are in the inverse Compton regime, so the electron is moving. And we can find that the energy loss, actually the dE over dt, so basically the energy loss by the fact that the electron is radiating, is found by sigma t, c gamma squared, 1 plus beta squared 3u radiation. So this is the energy loss just by the fact that the electron is emitting radiation. But this is not the final energy loss by the electron, okay? Because the real final, let's calculate first the inverse Compton power that actually is equivalent of the energy loss of the electron. This is actually equal to basically the power, the emitted power of radiation, and so the final energy density of the photon, minus the initial energy density of the initial photons. So the energy loss of the electron is the difference between the density of final photons with respect to the density of initial photon. Okay? So if you do this, so basically you evaluate this as sigma t, c u prime radiation, that is the initial one, minus sigma t c u radiation, that is the final one, you find the proper results for the radiation power or energy loss by the electron that is given by this equation here. So the electron energy loss, or the power, in this case is the same thing, is proportional to gamma squared. So it means that it's proportional to the electron energy to the second power, is proportional to the Thomson cross-section, and to the energy density of radiation. So if you have a location in the galaxy where the interstellar radiation field is larger, for example, the galactic center, you have more energy loss and more power of inverse Compton. If you increase the electron energy, the radiation is larger, the energy loss is larger. Beta is roughly equal to 1, so it can be neglected. But in this case, we were just using the basically the Thomson cross-section. We were not calculating the full calculation with the Klein-Nishina cross-section. In the case of the Klein-Nishina cross-section, unfortunately, the equations are a bit more complicated. So the energy loss is the integral in the initial and final energy of the photon. So epsilon is initial, epsilon 1 is the final. This is the rate of scattering due to the inverse Compton scattering. This is the cross-section differential in final energy and angle. And the final equation for the energy losses is given by this double integral in photon energy and in Q, that is a parameter here that depends on the final energy. Or in the Thomson regime, we can find something easier to understand that is roughly the same that you have here. So gamma squared is the proportionality with energy, and the integral of this n gives the radiation, the energy density of radiation. Instead, the power is not the same thing of the energy loss if you just make the full calculation with Klein-Nishina, because the energy loss you have to integrate over initial and final energy of the photon. Instead, for the power, you just have to integrate over the initial energy, because the power depends on both the energy of the electron and the final energy of the photon. Also, in this case, using the full Klein-Nishina calculation, it's more complicated than the Thomson regime. But just to show you some results about this is the power for inverse Compton on the three different components of the interstellar radiation field. So the red is the CMB, the blue is infrared, and yellow is the starlight. The two curves are for two different cases where you use a black body approximation for the interstellar radiation field. And instead, if you use the full calculation using the right energy density, you get the black. So using the black body can give you some, you can miss some interplay between the different components, but it's roughly the right calculation. It gives the bulk of the result. What is very important to show here is that even if CMB is the lowest component talking about energy, because the CMB is peaked at low energy with respect to sunlight and infrared, actually CMB is the main target for very high energy electrons. So for Hawk, the discovery of very high energy gamma rays, this Hawk discovery is basically due to electrons and positrons scattering on the CMB. Okay, so the scattering of the CMB is the main component for very high energy gamma rays around pulsars. Okay, now I would like to spend also 1 minute talking about this plot. This is the ratio between the inverse Compton power with respect to the peak of the power as a function of electron energy and photon energy. So if we have to fit the Hawk discovery, so for 1 TeV photon, the electron energy is roughly few tenths of TeV. Okay, so whenever you're talking about discovery of gamma rays beyond the TeV, basically you're reaching tens or hundreds of TeV for the initial electron. So if you reach a detection, let's say of 100 TeV for the photon, you are almost reaching the PV scale for the electron. Okay, and Hawk and LASO are actually detecting photons that reach almost hundreds of TeV for the gamma rays. So this implies that pulsar wind nebulae are actually PV accelerators. So these are very, very powerful accelerators of electrons and positrons. Okay. Okay, now let's talk briefly about a few properties about of pulsars. So pulsars are rapidly spinning neutron stars. So they have some rotational energy. The rotational energy can be evaluated with classical mechanics calculation using the momentum of inertia and the period. The momentum of inertia for a sphere is 2 times the mass r squared over 5. And so for the Crab Nebula, that is one of the most famous pulsars, the momentum of the inertia is an extremely large number, and if you plug in these numbers into the rotational energy, this gives roughly 10 to 49 ergs. So the rotational energy of a pulsar is an extremely large number that is not that far from the one of the supernova remnant. Okay, so it's reasonable to think that pulsar wind nebulae accelerate positrons. But during the rotation, the pulsar is emitting particles with very large multiplicity. So for every production of pairs of particles, it can generate a multiplicity of 10 to 3, 10 to 4 particles. And so for every particle emitted, there is a loss of energy. And so actually, there is a negative variation of the rotational energy. And this change in time of the rotational energy is also called spin-down luminosity. And this spin-down luminosity is proportional to the momentum of inertia, the derivative of the period in time, and is inverse proportional to the cube of the period. For example, for the Crab pulsar, this is 10 to 38 erg per second. So this means that every second, while it is rotating, the Crab pulsar emits 10 to 38 erg. So if a fraction of this energy goes into positrons, you can imagine how much pulsars are important for the acceleration of particles. In particular, the E dot, so the spin down luminosity, is related to the power of radiation. So we can write that the power of radiation should be equal to the spin down luminosity. We can use here the Larmor equation for the power radiated by a particle under a magnetic field. We use the equation we found before for the spin down luminosity. And then we can reshape this equation to give, for example, this equation that relates P and P dot. So P dot is equal to 8 pi squared radius 6 B sine of alpha okay. So the product of the period for the derivative of the period, that is one of the, these are the two main characteristics measured by telescopes for pulsars, depends on the momentum of inertia, the radius, and the magnetic field. In fact, typically, pulsars are described in this plane of the derivative of the period and the period. That is exactly what I showed there. So in the y-axis, you have the derivative of the period. You have these green lines that are different layers of magnetic field. Here it is 10 to 12, 11, 10, and 9. And you see that these data are the detected pulsars. And here you have millisecond pulsars for periods between a millisecond and 10 of millisecond. If the period goes beyond the tens of milliseconds, you have young pulsars, or also called normal pulsars. These two populations are very different populations because these are younger, okay? When they rotate for a lot of time, after some time, they start to lose all their energy. So this means that the period starts to increase, the derivative of the period goes down, so the pulsars goes in this direction. And when they cross this black line, they are not emitting anymore non-thermal photons. Basically, they die. But when they die, their life is not yet ended, because they can meet a star, a companion, and they are recycled to a millisecond pulsar. So millisecond pulsars are recycled pulsars that take material from another star or a companion, and they are recycled to very, very powerful pulsars. And this happens typically after some time. This is why millisecond pulsars are typically older. Pulsars are detected mostly on the galactic plane. Young pulsars are mostly located on the disk. Instead, millisecond pulsars can be located also at higher latitudes. The reason is, as before, millisecond pulsars are older. They have a kick velocity, so they move in the galaxy even at 100, 200 kilometers per second. So after several kilo years, they can travel in the galaxy also by several kiloparsec, okay? So they start their life on the galactic disk, where you have supernova remnants, and after kilo years, they start to move away from the galactic disk. Okay. So After some time, they can, so you probably remember what I said about the supernova explosion. You have the supernova explosion. In the center, you have the pulsar, or the neutron star. The supernova ejecta move away. After some kiloyear, they hit interstellar medium. The pulsar starts to create pairs of particles, and this pair of particles produce a nebula that is called the pulsar wind nebula. This pulsar wind nebula at the beginning is concentrated around the neutron star and is full of relativistic particles. But at the beginning, this system is stable. So the pulsar wind nebula keeps contained inside each the positrons and the electrons. But when the shock wave hits the interstellar medium, it's reflected, and you have the reverse shock. The reverse shock propagates towards the center and hit the pulsar wind nebula. After hitting the pulsar wind nebula, the reverse shock accelerates the particles trapped inside the pulsar wind nebula, and the positrons and the electrons are accelerated and ejected into the interstellar medium. This is the first mechanism for acceleration of positrons from pulsar wind nebula. But after kiloyears, the pulsar that moves at 100 kilometers per second can travel a lot of parsec. And after some time, the pulsar exits escape the shock wave of the supernova and becomes an isolated pulsar. So this is what happens to me for middle-age pulsars with an age at least of 40 kiloyears, where this example is the Geminga pulsar seen in X-rays. So the pulsar is moving in this direction at 100 kilometers per second, is ejecting pairs of particles. You have these tails of particles ejected that are ejected in interstellar medium. And these tails are actually visible in X-rays and in radio. Here the angles are very, very small. So here we're talking about 1 arc minute. So this is impossible to see in gamma rays. What we can see in gamma ray, when we model a pulsar, you can use the pulsar emitting positron and inverse Compton. And this is the expected gamma ray signal at different energies. If you go higher in energy, the gamma ray emission is most centered in the center of the pulsar because of the energy loss. And this is when you don't take into account the motion of the pulsar. Instead, when you take into account the motion of the pulsar, this is what you have. This is where the pulsar is now. This is where the pulsar was in the past. And for GeV or tens of GeV gamma rays, actually most of the emission is not where you have the current location of the pulsar, but it is where the pulsar was in the past, because electrons were generated kiloyears ago. They started to generate photons. These photons travel straight without diffusion, and they are detected before the electron, new freshly accelerated electrons, are ejected from the center. But when you go at higher energy, so the energies of TeV scale, this effect is not visible. So this effect of the proper motion of the pulsar is not important for Hawke and the Cherenkov telescope array measurements, while instead they are important for Fermi-LAT. Okay, now very briefly, I will show you also something about extragalactic sources. Extragalactic sources like active galactic nuclei are very important for the production of gamma rays, actually for the emission of radiation from radio to gamma rays. AGNs are actually the most abundant species in Fermi-LAT catalogs. There are currently of the order of 3,000 or maybe even more AGNs. The most important AGN are radio loud, that are roughly 10%. The luminosity of radio loud AGN is larger with respect to radio quiet. And they are divided into blazars and radio galaxies. So blazars are active galactic nuclei where the jet is aligned towards the observer. Okay, the jet is really pointed towards the Earth. Radio galaxies instead are galaxies for which the jet is misaligned. And the misalignment make radio galaxies less powerful with respect to blazars. Other objects that are relevant for gamma rays are star-forming galaxies and radio galaxies. The problem is that these two sources are less numerous with respect to blazars. And so the calculation of the gamma ray flux from undetected objects is more difficult. And you typically have to consider correlations between gamma ray luminosity and infrared for star-forming galaxies and with radio for radio galaxies. The reason we study this correlation is that for infrared catalogs, star-forming galaxies are much more numerous, and for radio galaxies, radio catalogs are much more numerous. So since we have very good estimate for the properties of radio galaxies in infrared and, star-forming galaxies in infrared and radio galaxies in radio, we use this correlation to estimate the cumulative flux of these two source populations. And if we study the unresolved gamma ray sky by Fermi, so this is an isotropic emission that we see in the extragalactic sky, most of this emission is probably due to unresolved blazars, radio galaxies, and star-forming galaxies. In fact, you see the one for radio galaxies in orange. Blazars is green plus gray, and star-forming galaxies is the pink. As you can see, the sum matches quite well the unresolved contribution from Fermi. And this is, of course, important for dark matter because if you have something unresolved by an experiment, some part of the contribution could be due to dark matter. The last thing I wanted to mention is that in the center of the galaxy, several groups have found an excess of gamma rays. This is called the galactic center excess by Fermi. This excess is actually a tiny part of the total data. So the excess are these triangle green dots. That is basically a few percent with respect to the total data. So if you want to claim that you detect something bright in the center of the galaxy, you have to know the interstellar emission of gamma rays less than a few percent. Otherwise, if you have fluctuation of the interstellar emission above a few percent, you can claim that this detection is actually affected by your uncertainties. The important thing of the galactic center excess is that the flux as a function of angle, the black dots, are compatible with the expectation for numerical simulations, so are compatible with the slope of the Navarro-Frankel-White. We will talk more about this in the next few days, but just wanted to show you already the data. The black data points are from a paper I made a few years ago, and the blue curve is the expectation for Navarro-Frankel-White with a slope of 1.2, that is something reasonable. So the gamma ray sky is very interesting for the search of dark matter, but you have to be careful that you really need to know very, very carefully your astrophysical sources, supernova remnants, pulsar wind nebulae. As I show here, it's very important to know well, and very, very well, the model behind the interstellar emission of gamma rays, so how cosmic ray collide with interstellar medium and generate photons. because the kind of excess that you can find are just a few % of the total data, okay? Currently, the uncertainties on the interstellar emission are dominating the systematics related to the dark matter search. Okay, stop here. Do you have any question? Yeah. Yeah, so the dust cloud is taken into account because basically you use the dust cloud as a tracer for the pi zero production. So when you calculate the pi zero production, but also the Bremsstrahlung production of photons, you use these observations of the distribution of clouds and the emission lines of the dust, and you convert the distribution of gas into a gamma ray flux, convolving in a similar way that I said before. Okay, so the emissivity of pions is proportional to the density of interstellar medium, and then you have the integral of the cross-section multiplied for the flux of the protons. Here is the place where you put the dust distribution. Okay, and typically the CO, the different components, the molecular hydrogen, the ionized hydrogen, all the different elements of the dust is observed by multi-wavelength observations where they try to detect emission lines. With this analysis, you have an estimate of the distribution of gas that you plug in here to get the emissivity. Okay. Yeah. Ah, you mean the absorption of gamma rays? Yeah, this is also taken into account in the calculation, absolutely. So basically, you can do a 3D calculation of the gamma ray emission, including also absorption by dust. Yeah. Other questions? Okay, if not, we can stop here. Great.